Next topic, fouling factor. The performance of heat exchangers usually deteriorates with time as a result of accumulation of deposits on heat transfer surfaces. The layer of deposits represents additional resistance to heat transfer and causes the rate of heat transfer in a heat exchanger to decrease. The fouling factor RF, the net effect of these accumulations on heat transfer. So, fouling factor is the main culprit to decrease the heat transfer rate in a heat exchanger, and this is the net effect of these accumulations on heat transfer. There are two common types of fouling: precipitation of solid deposits in a fluid on the heat transfer surfaces, corrosion, and other chemical fouling. The overall heat transfer coefficient needs to be modified to account for the effects of fouling on both the inner and the outer surfaces of the tube. For an unfinned shell and tube heat exchanger, it can be expressed as R is equal to 1 by HI AI plus RFI AI for inner, ln d outer by d inner divided by 2 pi KL plus RFO AO for outer, and plus 1 by HOAO. This is equation 8. Here is RFI, that means fouling factor for inner, RFO, fouling factor for outer, are the fouling factors at those surfaces. It means RFI for inner surface and RFO for outer surface. There is a problem. A double pipe shell and tube heat exchanger is constructed of a stainless steel K is equal to 15.1 watt per meter degree Celsius, inner tube of inner diameter DI is equal to 1.5 centimeter and outer diameter DO is equal to 1.9 centimeter, and an outer shell of inner diameter 3.2 centimeter. The convection heat transfer coefficient is given to be HI is equal to 800 watt per meter square degree Celsius on the inner surface of the tube, and HO is equal to 1200 watt per meter square degree Celsius on the outer surface. For a fouling factor of RFI is equal to 0.0004 meter square degree Celsius per watt on the tube side, and RFO is equal to 0.0001 meter square degree Celsius per watt on the shell side. You have to determine number A, the thermal resistance of the heat exchanger per unit length, and number B, the overall heat transfer coefficients UY and UO based on the inner and outer surface areas of the tube respectively. There is the pictures including all this data from the question. Here comes the cold fluid, outer layer of fouling, tube wall. This is inner layer of fouling, and here is the hot fluid. So this is an exchanger. Cold fluid comes through this, hot fluid comes through this. D inner for this 1.5 centimeter, H inner is equal to 800 watt per meter square degree Celsius, and fouling factor is 0.004 meter square degree Celsius per watt for inner, and similar there are some data of the outer surfaces. Solution: the heat transfer coefficients and the fouling factors on the tube and shell sides of a heat exchanger are given. The thermal resistance and the overall heat transfer coefficients based on the inner and outer areas are to be determined. Assumptions: the heat transfer coefficients and the fouling factors are constant and uniform. Analysis: number A, the schematic of the heat exchanger is given in figure 1311. The thermal resistance for an unfinned shell and tube heat exchangers with falling on the both heat transfer surfaces is given by equation 13.8 as R is equal to 1 by UAS, that means 1 by UIAI is equal to 1 by UOAO is equal to 1 by HIAI plus R Fi by AI plus ln d naught by di 2 pi kl plus Rfo by AO plus 1 by HOAO, where AI is equal to pi DIL, that means pi given value di 0.015 meter, L means 1 meter, is equal to 0.0471 meter square. And same for that, AO, outer surface area, is 0.0597 meter square. Substituting, the total thermal resistance is determined to be R is equal to 1 by 800 watt per meter square degree Celsius into 0.0471 meter square plus 0.004 meter square degree Celsius per watt divided by 0.0471 meter square plus ln 0.019 divided by 0.015, the value of d outer and d inner, divided by 2 pi 15.1 watt per meter square degree Celsius into 1 meter plus fouling factor for outer surface 0.0001 meter square degree Celsius per watt divided by 0.0597 meter square plus 1 divided by 1200 watt per meter square degree Celsius into 0.0597 meter square. So after calculation, we got 0.02654 plus 0.00849 plus 0.0025 plus 0.00168 plus 0.01396 degrees Celsius per watt. This is the unit. So R is equal to 0.0532 degrees Celsius per watt. Note that about 90% of the total thermal resistance in this case is due to fouling, and about 5% of it is due to the steel tube separating the two fluids. The rest, that means 19 plus 5 is equal to 24, so 100 minus 24 is equal to 76. So the rest 76% is due to the convection resistances on the two sides of the inner tube. Number B, knowing the total thermal resistance and the heat transfer surface areas, the overall heat transfer coefficients based on the inner and outer surfaces of the tube are determined again from equation 13.8 to be like that. EY is equal to 1 by RAI. We have all this value, so 1 by R is equal to 0.0532 degrees Celsius per watt, and A inner means 0.0471 meter square. So after calculation, we got EY is equal to 399 watt per meter square degree Celsius. Similar to that, UO, that means for outer, 1 by RAO, 1 by 0.0532 degrees Celsius per watt into